Welcome back. So let's now look at the next statistics concept we need, namely the idea of standard deviation, or in the quantum mechanics language, uncertainty. So you might have talked about standard deviation in the context of a lab or experimental data before. Let me illustrate what I mean with a picture. So imagine you had some measurements. Maybe you were to measure the height of a group of people, like maybe the students in our class, and you might get something that looks like this. So if I take a histogram, so if I plot the number of measurements on the vertical axis versus height, we might get something that looks like this. We're in our class, right? We're all more or less not too far off from each other. Maybe we get something that looks like this. So there's some sort of narrowish distribution. Well, suppose we were to consider another measurement. So instead of the people in our class, we were going to go and take the entire population, maybe including like babies as well as NBA players. We might get a wider distribution. So maybe it looks like this. And I think you can visually see that the distribution here is wider than the one on the left. Now, they might still have the same sort of average, if I sort of eyeball this value, but they're clearly different in their widths. That width idea is what the standard deviation quantifies. So in particular, so we have a larger spread here, and we quantify the standard deviation in the following way. So I'll just show you the two notations we might use. For quantum physics, we'll write delta n. Very often in statistics or in a lab context, you might see that written as lowercase Greek sigma sub n. And we define it in the following way. We define the square of this as the average value of n, of the quantity n minus its average value squared. Now, just a piece of terminology. Delta n is what we call the standard deviation. The thing that I've actually written out here, this we define as the variance. So that's delta n quantity squared. Now it's important to think about why we define it this way, right? We're looking at the average sort of deviation from the average value. So we're going to take n and see how far it is from the average. But why do we want to find the average of this entire thing squared. Well, if you think about it for a little bit, you might realize that if I have a nice distribution like this, I'm equally likely to be bigger than the average as I am to be smaller than the average. So if I just try to average n minus the average value of n, I'm going to get 0. What I need to do instead is to square this, which gives me something that's always positive, and then I can meaningfully relate this to the width of my distribution, right? So for a really wide distribution, you might imagine how you'd get these larger differences between n and its average value, whereas for a skinny distribution, this thing here might be small, which is why the standard deviation is a useful measure of the width. Now, there's a useful theorem about the standard deviation. Usually it's not as convenient to calculate it directly from the definition, and it's often going to be easier to use this theorem. I'll sketch a proof after I state it. Namely, the theorem says that the variance, so delta n squared, is going to be given by the average value of n squared minus the average value of n squared. So this is often how we're going to go and calculate standard deviation, since we can usually calculate without too much trouble the average values of n squared and n. So here's a sketch of the proof. I believe Townsend does work this out. And this is going to just come from applying the definition. So the definition says that, right, it's the average value of n minus the average value of n squared, and so the reason for this is by the definition. So if I go and multiply this all out inside the averaging brackets, I get, so if I FOIL this, I get n squared. I get my cross term, so I have a minus 2 average value of n times n. And then I have minus average value of n squared. So this is multiply out. Now, we're going to have to invoke some properties of averages. I'm going to not prove those, but hopefully it's plausible to you that I can break the average of all three of these terms added together into the sum of the averages of each of my terms. So if I'm allowed to do that, then this will turn into average value of n squared. If I'm allowed to subtract, then I'll get the average value minus the average value of 2 times average value of n times n minus the average value of n squared. Okay? Now, here's the thing, right? So notice that the average value of n is really just a constant. It's not going to change for different values of n. The average is well defined. So it turns out I can actually just get rid of these outer averaging brackets here. So this term, the third term, just turns into minus minus average value of n squared. I can't really do anything with this first term over here, so that's going to still be average value of n squared. But now with this term, notice that 2 is a constant. Also, as we argued before, average value of n is also a constant. If it's plausible that I'm allowed to factor these constants out, then I get minus 2 average value of n pulled out, and then all I'm left with is the average value of n. Whoops, I made a sign error. There should be a plus over here. And so if I do all of that, right? So now notice that this is really average value of n squared minus 2 average value of n times average value of n, which is just n squared plus n average value of n squared. And so simplifying this, we end up with n squared minus, so average value of n squared minus average value of n squared, and that completes the proof. Now, let's have you look at an exercise involving calculating the standard deviation of n when you roll a 6-sided die. Alright, so you've thought about calculating the standard deviation in n for rolling a 6-sided die, and you could calculate this either by directly applying the definition, but it turns out to be easier to use the theorem, at least I think. We already had, from earlier in the class, we had already calculated the fact that the average value of n for a die was 7 halves. So to use the theorem, all we need to do is calculate the average value of n squared. So find so I'll just say use theorem. Okay. And that, again, applying the definition of an average value we talked about, so that's going to be 1 squared times the probability of 1, which is 1/6, plus 2 squared times the probability, and I won't write out every single term, the plus dot dot dot, and the last term, of course, is 6 squared times 1/6. Again, we have the same probability here of 1/6, so I can factor that out. And I'm going to get 1 plus 4 plus 3 squared is 9, plus 4 squared is 16, plus 5 squared is 25, plus 6 squared equals 36. And if I go and simplify this here, I end up with 1/6, let's see, we have 5 and 9 is 14, 14 plus 16 is 30, 30 plus 25 is 55, and then 55 plus 36 is 85 plus 6, or 91. So we have the average value of n squared equals 91/6. Then by our theorem, our variance delta n squared is given by average value of n squared minus the average value of n, quantity squared, which is going to be 91/6 minus 7 halves squared, which simplifies to, that's 91/6 minus 49/4. And now we just have to simplify this. So we have, delta n squared. So that's going to be 182 over 12 minus 40. So we'll get a common denominator. So 49 times 3 is 147. And this gives us 12. So let's see, 2 minus 7 is 5. 8 minus 4 is 4. We have a 3 here. Yep, that's a 35 over 12. That doesn't really simplify nicely, but then we can then take the square root to find that the standard deviation or uncertainty, then n, is going to be square root of 35 over 12. Now, in quantum physics, what we often care about is the uncertainty in x. If you've been reading ahead, you might sort of get the hint that we're heading towards the Heisenberg uncertainty principle. So in QM, we care about the uncertainty in x, delta x, and to find it, it's often easiest to use the theorem. Usually find via the theorem we just did used for the die rolling example. So namely, the uncertainty in x is going to be the average value of x squared minus the average value of x itself squared. And we find this using the wave function. So this is going to be the integral of x squared times our probability density, psi of x t modulus squared, minus the average value of x, which you already know how to find. That's the integral of x times our probability density, and I need to square the entire thing. So, today we have learned about a little bit about statistics. We've practiced also using calculating normalization. I want to end today with an exercise that ties together all of the ideas we've talked about. So I'll project that slide now. Let's have you think about it, and then when we come back for the last video, I'll talk through how I solved this.